So we can continue. So let's start with your process diagram. So how we can try to get all the process for your desalination plant, and how you can go one by one for the detailed design. So you can see first the seawater intake. So just to get the seawater, it's a very big volume you can have, and we just simply bring the seawater. And first step is chlorination. The seawater contains a lot of bacteria and algae or some microorganisms. So if we don't kill all of them, so what happens is a lot of biofouling in the pipeline, also pumping system, also BAVE, like the monitoring sensors, they keep accumulating on the so many surfaces. So we have to kill all of the microorganisms. Otherwise, you have growing a lot of muscles, growing a lot of so microorganism inside the plant. So we want to kill all of the microorganisms first using chlorination, and then we need to go for the ferric chloride. So sometimes you have a very high turbidity seawater because a lot of rainfall, and then your soil washed out to the ocean. So a lot of the very strong wind and the strong waves and tide. So you have a lot of turbidity water. So in this case, you need to use a coagulant, which is ferric chloride, and you can remove all the turbidity water. And pH adjustment. So seawater pH is 8 because of a lot of alkalinity inside the seawater. Especially, you know that the seawater, we have CO2. The CO2 in the air. So CO2, if we have a more CO2 because of this climate change, the CO2 dissolved in seawater, and you have a very serious problem. For example, like this is the CO2 concentration, and this is bicarbonate, and this is carbonate. So in seawater, normally we have a pH 8, so which means bicarbonate concentration is the highest. So bicarbonate can easily combine with the calcium. So I'm sure that a lot of people like the crabs or lobster. The lobster surface is the calcium carbonate. So they combine with the bicarbonate with the calcium. Calcium replaced with the H. So calcium carbonate, we create a lot of strong your skin of the lobster or muscles. Most of like a coral, calcium carbonate is very important because most of the seawater, your food is from this bicarbonate with calcium carbonate, magnesium carbonate. But if we have a more CO2 because of this climate change, a lot of industrial activity, so what happens is the pH will decrease. The pH decrease and decrease. So we cannot have any more lobster in the future. Yep. And we cannot get any crops, even a lot of calcium carbonate related material cannot be produced like coral. The Great Reef Barrier is in danger because of this kind of CO2 concentration. You cannot make calcium carbonate, which is the one of the useful material for our seawater lives. So this pH is 8. The problem is pH 8 is a high concentration of OH. So OH minus can easily combine with the calcium, magnesium. So you have a calcium hydroxide, magnesium hydroxide. So we need to reduce the pH to have a less inorganic scaling. So if you have a very high pH, your pumping, even your membrane, even your our sensors, there are a lot of inorganic scaling will accumulate. So like us, that we have some kidney, like your kidney has calcium carbonate or calcium sulfate, calcium phosphate. So some people, you have a kidney stone. Kidney stones are from this calcium carbonate and calcium phosphate because of they're combining easily with the high pH. The same as seawater. So high pH 8 is not really suitable to have a lot of inorganic scaling, like a stone in your pipeline and reverse osmosis. So we reduce the pH to 6, from 8 to 6. So you can put the H2SO4 or HCl to adjust your pH to avoid the inorganic scaling. So after this pre-treatment, we have a dual media filtration to remove some of the larger objects and then protect your seawater reverse osmosis membrane. Also, you need to put the anti-scalant. So what's the anti-scalant? The anti-scalant is like, okay, this kind of material. So we have anti-scalant. So if you don't use anti-scalant, the calcium carbonate, calcium sulfate, magnesium carbonate will be accumulate on the membrane, outer surface, because we keep desalinated water. So pure water is permeate, and then leftover calcium, carbonate, magnesium, they will keep accumulate on the surface of the membrane. And you have this kind of calcium carbonate, inorganic scaling, and calcium sulfate, inorganic scaling on the surface of the reverse osmosis membrane because of very high concentration. And we need to put the anti-scalants, which are surface active materials that interfere with the precipitation reaction in 3 primary ways: threshold inhibition, crystal modification, and dispersion. So sodium hexametaphosphate is a hexanomer, the composition, Na phosphate. And you can see that this material, so you have a calcium, let's say carbonate, they need to grow, like inorganic scaling, crystal is keep growing, make a larger stone. But if you add this sodium hexametaphosphate, so they interfere with calcium. Calcium combined with this SHMP, like some organic compound, and then you cannot grow continuously like this size. The calcium carbonate, you can have this kind of big size. But if you add the anti-scalant, so they avoid your growing of the crystal on the membrane surface, which means you will clog completely your membrane surface, which cannot get any water flux. So that's the anti-scalant. How about the dechlorination? The chlorination, we try to kill all the microorganisms, and we need to have a dechlorination before reverse osmosis, because reverse osmosis is like a polymer, so they can be easily oxidized using this chlorine. So how we can make sure dechlorination? So everybody knows that the chlorination. So when you are in the swimming pool, so you have a very strong smell in your swimming pool, especially when you have a summertime. Summertime, the chlorine is volatile, so they evaporate. So if your temperature inside the swimming pool is very high, so your smell is more toxic, because chlorine is more volatile in your air. So you can have a more smells in the swimming pool. So how this chlorine can give a dechlorination? So in the chlorine here, so before the reverse osmosis, the dechlorination can be processed two steps. So one is the addition sodium bisulfite. So we just put this sodium bisulfite, which is this compound, NaHSO3, and chlorine combined with this one in the water. And chlorine can be active chlorine moved to the HCl. So chlorine is a very strong oxidant. So when they are together, like a Cl2, but if they are like a chlorine ion, like a Cl single ionized form, so this is the very safe. It's a no more oxidants. Yep. So this compound will be making this HCl, chlorine and Cl2 move to the Cl minus ion, and we can have a very good dechlorinated water. Otherwise, this Cl2 will attack your outer membrane. Outer membrane is a polymer, like a nylon textile. So outer membrane will be damaged because of chlorine, and then you can just remove all the skin layer of the membrane, outer. So we need to dechlorinate your water and pass through reverse osmosis. So this is the reverse osmosis, and we can go next step, post-treatment. Post-treatment with lime. The lime has also calcium hydroxide and fluoride, chlorination again, because of you need to make your water very much safe. So while traveling to your water, so chlorine will continuously kill your microorganism. So if you just turn on the tap water, in fact, you're drinking chlorine almost less than 1 milligram per liter. So your chlorine is still there inside the tap water, and this chlorine, when you have a less concentration, that's fine. You can drink as it is. But if you have a very high concentration, sometimes, so you cannot control your chlorine concentration. So your smell of the tap water has a very strong chlorine taste. So I'm sure that some people, they cannot drink the tap water because of sensitivity of the chlorine. So some people are very sensitive on chlorine taste, so that they have bottled water. So what's the big difference between tap water and bottled water? Bottled water doesn't have any chlorine. So bottled water is from spring water in rural area or remote area, and they just pumping out from groundwater or just from the mountain. So they have like a very clean water coming through the your surface water, and they just use the UV without any chlorine. So you have a bottled water, you cannot have any chlorine taste or smell because they don't add any chlorine just to put the UV and kill all the bacteria in your drinking water, and then they just fill your bottle. So your bottled water is UV treated disinfection, and this tap water is mainly chlorinated disinfection. So that's the very big difference, because some people believe the chlorine is a very strong oxidant combined with the organics, which means they believe they create the trihalomethane or haloacetic acid, acetic acid, which means chlorine combined with the organics, and then they create the carcinogenic compound. So a lot of people, they don't like tap water because still tap water has a little bit of carcinogenic organic compound mixed with, and then tap water, there is no chlorine, and then UV treated water. So UV means, you know, in Australia, we have a lot of cancer, skin cancer, because of the UV, because UV attacked our skin, and then UV will change your DNA. So every cell, you have to continuously divide, and then you have to die and then survive again. So that's the cell. So they have like a DNA continuously revive your skin cell, but the UV will attack your skin, and then they cut your DNA on your skin, and then you cannot get the new cell for your skin, and you have a skin cell. Skin cell is growing and growing. That's the reason why the UV will attack your bacteria, which is the DNA, so that they cannot continuously grow. So that's how they kill the bacteria inside the UV bottled water. And the chlorinated, if you put the chlorine in your hands, so you will melt your skin, because your chlorine has a very strong oxidant. The organic compounds will be dissolved. So slowly you dissolve your skin. So that's the two different way of the disinfection. So bottled water, tap water. So people ask you, what's the big difference? Big difference is chlorinated water is tap water. UV treated water is the bottled water. That's the reason why people have a confusion. Okay, is it bottled water is good or not? In terms of chlorine through halomethane of carcinogenic compound, bottled water is better. It's true, but because of this tap water has chlorination. But this chlorine is this amount of concentration is less sample. People believe the less sample, which means it doesn't really damage a lot. But every day, yeah, you drink tap water, yeah, boiled water. So people like boiled your water because of chlorine will evaporate. So when you boil tap water, the reason why, and then they remove the chlorine as a volatile. So make a tea or warm water will be much more safe than just normal tap water. So chlorination, it was discovered 100 years ago. The before we discovered chlorine, the people's average lifetime was around 40 years old or 50, middle of 45. But after the UK engineer developed chlorination to drink water, and then human lifetime increased to more than 30 years. So, as you know, the 100 years ago, most of people died before 50 years old because of they have a lot of contaminated water drinking and the pathogens. So, they easily die, contaminated by the water infected pathogen. But after we have a drinking water pathogen for chlorination, our life expectation increased more than 30. Now we are keep increasing like 83 years old. Now, after 50 years, we will have almost 95, 100. And now people try to change the bio clock to make younger rather than older. So that's the chlorination is the one of the best discovery in the world because this is the why we have a very long lifetime because of safe drinking water and we killed all the pathogen which we created the problem in our body system. So dechlorination is a way how you can have this one and then go for your SWRO and the remineralization. So post-treatment, so why should the desalinate water be remineralized? The low mineralized water have a very few adverse effects. The high corrosion potential. So if you don't have a mineral, so your pipeline maybe let's say stainless. So stainless pipeline will be easily damaged. So we just say corrosion potential is much higher. So you know that your pipeline of the tap water is mostly stainless. So they are like a copper or stainless, which is a very strong corrosion potential. But if you don't have this mineral, you have a very strong corrosion potential. So that we need to put this remineralized water and dietary deficiency causing risks of this heart disease and this kind of compound also like magnesium or some of the mineral. So we have to keep drinking together. Otherwise, you have some of the heart disease. And WHO recommends 10 milligram per liter of magnesium. That's why the Evian has 35 milligram per liter of magnesium. But some of the spring water has not much that kind of magnesium concentration. That's the one of the reason the Evian try to sell. They have a very strong the WHO recommended magnesium concentration and calcium. So Evian has both magnesium and calcium high concentration in the bottled water compared to the other bottled water. But it doesn't mean you have to drink Evian because you have a lot of calcium magnesium from your vitamin or your also food. So there are many food that contain the magnesium, calcium. So you have like a seafood, like anchovy has a very high concentration of calcium. Also you have a bone, your some of the meat has calcium, magnesium. So in fact, you can intake a lot of calcium magnesium. So it doesn't mean you need to have a Evian water to drink the calcium magnesium. So two solutions are widely used to mineralize and neutralize water. And the CO2, as I mentioned, the CO2 will convert to bicarbonate. Like depending on your pH, so you have a bicarbonate and calcite limestone, calcium carbonate, and magnesium oxide. And also you can put the sodium carbonate, which is the good mineral. So we can protect your pipeline. Also, it's good to have a healthy minerals, magnesium, calcium in your body. So that's why we want to put this one. And then calcium chloride and sodium bicarbonate also useful for your remineralization of the water. So that's the how we need to design your seawater desalination plant. So your assignment one, assignment three. The first question was, okay, to make a process diagram. So this is the process diagram. So you can change ultrafiltration here on behalf of dual media filter. Also, you can change some of the pretreatment if you like. Also, you can say that the sum of the post-treatment, the pretreatment, you don't have to include because of your water quality. And some of the post-treatment, you don't have to add or you don't have to include. So depending on your design, so you can change the pretreatment side and post-treatment side. So that's the how we can design for your seawater. And seawater annual operation and maintenance cost, mostly, as I mentioned, energy cost. So you have a lot of energy to produce the desalination. So every day, city desalination plant, you need to put the energy cost every day almost $300,000, only energy cost. And then they have also fixed cost, indirect cost, monitoring cost, and the maintenance cost, labor cost, chemical cost, waste cost. So there are membrane replacement cost. So altogether, so you have a lot of expensive operating and maintenance cost. So that's the what we have to do process diagram. Then terminology. So membrane design has a little bit specific terminology you have to learn. The flux. Flux is throughout per membrane area. So liter per hour per square meter and LMH. We just say LMH, liter. So you have 1 liter permeate for seawater in the 1 square meter, 1 square meter, 1 meter, 1 meter square meter of the membrane size, surface area. The water is passed through the 1 liter and then hours, per hours. So 1 hour you pressurize seawater and then 1 liter you collect with the 1 meter surface area of the membrane. So that's the how we just say LMH. So normally when you design your reverse osmosis, so we just calculate how many water you need. So when you design for your seawater desalination plant based on your scenario, you have to design for 250 megaliter per day. So how many membrane you need? And then how much water LMH you have to produce? And then how much pressure you have to push to produce your desalinated water. So that's the how you have to calculate. Like a 1 liter, 1 square meter, 1 hour. So you have this much of the water. So how many surface area of the membrane, how many pressure you have to apply, and then how many membrane module or element you need for your desalination plant design for 250 megaliter per day. So that's your question. So your second question of the assignment 3, design your banks, how many elements you need, how many surface area you need, how many module you need for your desalination plant design. So that's the question you have to answer for your scenario. So that's the flux and permeate. Permeate is water treated by membrane, right? And concentrate. Concentrate is like waste from the membrane. So you have pure water and very high concentration salt, brine or concentrate, we just say. And then how you can handle this one. And recovery. Recovery is very important. So you have 1 liter of seawater. You desalinated the seawater 50%. So you have a 0.5 liter of the drinking water. permeate water, and 0.5 liter of the brine, high salt water. So recovery. So you need to design recovery because the recovery is related to your osmotic pressure, your design of the applied pressure, and then how you can calculate this recovery. And TMP is a transmembrane pressure. Transmission is passage of the certain solute across the membrane. Opposite of the rejection, transmission is 1 minus rejection. So we just say unit, like a grouping of the membrane and vessels with common feed form, pumping, and controls. So you need to design for your assignment 3, 250 megaliter per day. So 250 megaliter per day, we don't design one unit. So let's say we design 25 units. So which means 25 unit, we have to divide by this 250 megaliter per day. So which means you need to design 10 megaliter per day, 1 unit. So you design based on your preference. So you want to design 250, you don't have to design all together. So use just the split, like 100 times or 25 times or 10 times. So make a 10 unit design or 100 unit design. So all combined, water will be whole capacity of your water design, right? So let's say unit. Unit will be, okay, 1 unit I want to design around 1 megaliter per day. So your target design capacity is 250 megaliter per day of the Sydney desalination plant. So multiply by 1 unit, 1 megaliter, multiply by 250. So you design 250 megaliter per day, 250 units. So you make a smaller because smaller unit will be easily you can design. Also, you can just make a contingency planning. Like if you break down 1 unit, you can have some standby and then make some redundancy of your unit. So you can have like some operation, maintenance, repairing, or some breakdown so that you can have a 10 unit, 20 unit. So you can make that kind of unit system. So unit will produce certain amount of your water desalinated. And elements is uh, like one module, which is individual membrane unit. Also module is the microfiltration, ultrafiltration, individual membrane unit. So let's say smaller module, like a 1 meter size of this is one element. So one element contains around 40 square meter of the membrane surface area. So this membrane, one element will produce around 100 liter per day. So 100 liter per day, one element. So how many element we need to produce the 250 megaliter per day? So we have to calculate one element. This RO membrane will produce the 100 liter per day or 20 LMH. And this module, how many we need to have this one? That's the exactly you need to answer your assignment 3. So how many you have to calculate? So this is the standard element we have. How many standard element you need a number, and then how we can get this design. And cassette and CIP cleaning in place. So you need to clean the membrane because of the inorganic fouling, organic fouling. So we need to have a cleaning in place, backwashing, enhanced backwashing. So that's the RO membrane design. So if you see the assignment 3, so specifically they asking how many elements you need for designing this kind of capacity. Then how many banks or how many units we just say banks or unit, you need to design for your seawater desalination plant. Then how many you have to have a surface area. So that's the you have to answer for your assignment 3. So this is the you can think about it. And that's the first question of the your assignment 3. Now let's go for quality. So what the quality will impact your design of the seawater. The seawater, let's think about when seawater start, when seawater formed. So what I remember I briefly discussed about when the Earth born. How old is the Earth? Do you remember the first day when I briefed your introduction of this 42991? So we mentioned about, let's think about seawater. Yep. The seawater, everybody likes seawater, right? Yeah. So why you like seawater? Because seawater give us food, like a sashimi and sushi, and a lot of fish, right? Also, seawater give us oxygen. You know that Amazon produced around 20% of world oxygen, but most of oxygen from seawater, because the seawater is around 70% of the Earth. And then a lot of seawater plants, like a seaweed or some fish. Also, they have a lot of photosynthesis inside the seawater, even corals. So they produce a lot of oxygen. So more than 70% of oxygen in the earth is from seawater. So they have a lot of seawater oxygen. Also, we have water, like a drinking water can be produced using desalination. Also, seawater creates all the living material, like a seawater uh, creates your DNA, RNA, and then all the necessary living material was synthesized in the seawater condition. Yep. So seawater provide much more than what we think. And this seawater was formed 4 billion years ago. The Earth's age is around 4.6 billion years ago. And after zero point 0.6 billion years later, so we have a lot of water from different source, and then complete our seawater. Already at the time, the seawater concentration 4 billion years ago and now is almost similar, because we had a lot of saltage already dissolved the seawater. That's the reason why the seawater concentration is very similar to 4 billion years ago and now. So we have a lot of salt inside, and the water quality parameters. So what's the inside of the seawater? For designing, we need to think about turbidity, total organic carbon, and salt index, density index, SDI, and total suspended solid, iron, manganese, silica, chlorine. temperature, oil, grease, pH, and carbon dioxide, bicarbonate, carbonate. Already we discussed about how CO2 changed depending on the pH, acidity and alkalinity, hardness, phosphorus, TDS, barium sulfate, strong sulfate, disinfectant. So these are the very important water quality parameters. So let's think about why these parameters are important to design. So let's say we design seawater desalination plant in Sydney. So you need to know about temperature. So what's the temperature change? So during summertime, Sydney seawater, what's the temperature? Yeah, nobody knows. Yeah, seawater during summertime. So when you're swimming during summertime in January, your seawater is very warm, right? What's the temperature of this water? The seawater is around 25 degrees. Yeah, during summertime and winter time. How about July? What's the temperature of seawater? Maybe 15 degree or 10 degree, right? So during summertime and winter time, so we have a temperature difference 10 to 15 degree. So what's the change of this one for seawater desalination? How this will impact? So when you design your desalination plant, you need to think about how much water can be produced. And when you design summertime desalination plant and wintertime desalination plant, so how this will make a change? That there are a lot of big change because, so let's think about you have a change of temperature. So what change will be water density? So you have increased your temperature, your water density is bigger, right? And then your cold water, your water density is changed. Water density change, how about viscosity? Water viscosity. So water is, let's say, 25 degree. So you put the one drop, and then your drop is flowing from your surface of the skin. So viscosity is change. So let's say 25-degree water drop, 10-degree water drop. So which will go faster to falling down? So which one is, okay, let's say running like together. So which one is faster to run? When you have a slope a little bit, and then 25-degree and then 10-degree water. So which one is faster? So you have a high temperature, has a less viscosity. So you can have a faster movement. So that's exactly the same. You have a water that you need to pass through your membrane. So you have a water molecule H2O zero point 0.3 nanometer size. The 0.3 nanometer size will pass through your membrane, yeah, your membrane, and the sodium chloride, sodium size is around 0.7 nanometer, and then your water molecule 0.3 0.4 nanometer will pass through your membrane, but your sodium chloride 0.7 nanometer cannot pass through your outer membrane. And then your water molecule at the temperature 25 degree, you have a faster to pass through. Then you have a low temperature, you have a less viscosity, you have a more viscosity, and then you have a less traveling time of the outer membrane. So 1 degree will change the 2% of your overall capacity of the flux. So you have increased 1 degree, so you have a more water flowing, water production, and you have to also calculate this kind of because water is keep moving there depending on the temperature. Also, when you design the Saudi Arabia, so you have a Red Sea or you have a Gulf Sea, so you have a very high temperature like a 35 degree or 40 degree in seawater temperature. So when you design the Alaska is a very cold area. It's less than 10 degree of your seawater. So you have a very big difference of temperature will make a very big difference of water flux. So how you can calculate? So there are formula you can calculate, but how we can calculate this kind of design, right? Okay, theoretically, you know that, okay, water temperature change and the viscosity density change and your production of the membrane will change. So how you can calculate for your design? Yes, there are formula you can use, but you don't have to know that kind of detailed chemistry. So that we have a software for this wave software. So you put the temperature, and this software will automatically calculate water viscosity and then water density. And then you can see how to design. Only what you can do, okay, you have a average temperature for whole year. Yep. And then you can design the average way of your design for your seawater desalination. That's the one you need. Also, turbidity, you have more, you need more pre-treatment to remove your turbidity and total dissolved solid. So we can also have a total dissolved solid. What's the very much different? So this is the water quality parameters. So tomorrow, yeah, we will discuss about this one. So you can see the temperature, the medium, what's the design, your temperature, and what's the maximum temperature you can design. So this software will tell you, okay, how much water flux you can produce from this kind of temperature variation. So you don't have to calculate all the detailed temperature variation. That's the reason why we need this software to have a very small parameters can be done with this software. So turbidity, depending on the NTU, what kind of pretreatment you need. So when you have a reverse osmosis, at least your NTU has to be less than 1 NTU. Also, total suspended solid, SDI, and this organic contaminant, organic content, because organic contents will create your biofouling, because organic is a very good food for your microorganism. So you have a biofouling or bio impact because of the dechlorination of the outer membrane. So you need to grow some of the microorganism which will impacted by this organic content. So tomorrow, okay, we have to put all the water parameter based on what you know from your scenario. So scenario, if you look at the appendix, so there is your water quality data is available. So you can utilize your a scenario given water quality information. So put the what's the water type, seawater, what's the water subtype, which means what kind of the pretreatment you will use. So you may have two options. One is ultrafiltration. The other one is pure media filtration, sand filtration. So you can select one of them. So you have an option here, membrane or media filtration. So you can provide all the necessary water parameters. Also, you need to put all the water quality. What's the sodium concentration? What's the calcium concentration? What's the magnesium concentration? So it's available in the appendix. So you put the data inside your scenario. So as much as the detail, you need to incorporate in this software because this will give you inorganic scaling potential, also your water flux potential, also your osmotic pressure potential, which will be required for your design of the seawater desalination plant. Yeah. So based on this, also one of question of the your assignment 3, what's the boron concentration? So whatever you put all the water quality here in the software, so you select your membrane in the software, and they will show you what's the final your drinking water quality. So you have to compare with the Australia drinking water guideline. So which concentration is high, which one is low, and then how we satisfy this drinking water quality. So water has a cationic compound, anionic compound, as well as neutrals. The neutrals are a problem because they are very difficult to remove because they have no charge. And no charge means they easily pass through the reverse osmosis membrane. But if you have charge, like brass, sodium, chloride minus, they can easily remove from the reverse osmosis membrane because of the Donan effect and charge effect. So that's the how reverse osmosis also impact your overall water quality. So you can see whatever your input you have, you will see all the output of your water quality data. So even heavy metals, any of your detailed compound, you can see from your software. So we will try this one tomorrow. So water quality is very important, which means so if you don't know water quality information, you cannot design the seawater desalination plant. Yep. So that's the we have to go, and this is the arrow. So reverse osmosis membrane is the most powerful desalination plant tool. So what's the arrow is how this guy can remove all the salt. So let's think about a little bit of chemistry, how this reverse osmosis have developed and then grown for the commercial opportunity. So this membrane is developed almost in 1950. The arrow membrane, so they, like, there are a lot of textile. So some of them, they have a nylon textile, which is not easily, you can protect all the wind and the water. So nylon is one of the very strong textile. So people initially believe, okay, this nylon as a material, they put the seawater there, then pressurize, and then they see what's coming out the other side. So one researcher, tried to put the nylon his jumper and then pressurize seawater and then look at what's the the other water coming out as a filtration. So he developed, oh, this is a reverse osmosis membrane, which means opposite of forward osmosis. So forward osmosis, reverse osmosis. So they are contradictory each other, and they developed the reverse osmosis, which means reverse osmosis. So you reverse osmosis, and then initially they believe this pressure is too high. You need to put very high pressure. So you need the energy around 10 kilowatt hour per cubic meter required. That's why at the time, the Saudi Arabia, Middle East country, they like to have a seawater desalination. So like a boiling. Boiling is the easiest way. So you boil the seawater. So you collect your distilled water and you can drink. So they have a lot of petrol. So petrol can be used to boil the seawater. So petrol, they utilize the petrol as a desalination for distillation. But R was competing 70 years ago, initially membrane. So membrane processed 10 kilowatt hour. But at the time, the petrol price was very, very cheap. So just boiling seawater, and then you can just produce the drinking water. Also, process is very simple, right? So at the time, they use the distillation water. Why do we have to use RO? Because it's complicated. Also, a lot of pressure you need. You need those RO membrane. So they didn't like it initially. And you remember 1960, we had a oil shock. So suddenly they increased the oil price because of some political issue. Also, some of the Middle East country, some war happening there. So there are several oil shocks. To increase the oil price is very high. That's why distillation was not cheap enough. So seawater desalination, RO, reverse osmosis, start further develop. And then another breakthrough was this uh, reverse osmosis. The Dow Chemical, they have a very simple method to produce RO membrane using polyamide. So they have a polyamide interfacial polymerization to make a very large scale of RO membrane, very cost effective. And it was one of the very good breakthrough. And then second breakthrough was the pressure exchanger. So utilize the 60 bar pressure. At the time, they didn't really change your pressure exchanger. Like a heat exchanger, you have to observe the heat. There you can save your heating cost. Also pressure exchanger was developed 1990s. And then you reduce your overall price of your energy cost from 10 kilowatt hour per 4 kilowatt hour. So distillation was 10 kilowatt more than 10 kilowatt hour for energy consumption because of the heating. And then RO energy consumption was significantly improved 1990 because of pressure exchanger, 4 kilowatt hour per cubic meter. That's the reason why since then, a lot of people, okay, we want to go for RO, reverse osmosis membrane. So we have a seawater reverse osmosis membrane, all our desalination plant in Australia. So no more distillation. So that's how we have a history. And this is the size of the reverse osmosis. So water molecule is 0.3 nanometers. So 0.3 nanometers, H2O. So H2O has to pass through the membrane. Then sodium chloride, sodium or salt, has to be stay in the membrane. Yeah. So we have developed polyamide membrane, which has around 0.6 nanometer of your pore size. So water molecule will pass through and salt can be removed. So that's the how we have a membrane. So you can see a lot of small atoms and molecule can be removed from this reverse osmosis membrane. So how this reverse osmosis membrane can remove the water molecule, or how we can design this one. So let me talk about non-porous membrane. The membrane thickness increase and permeate flux decrease. The active layer as thin as possible. So your membrane very, very thin, and then you can have a more higher water flux. And membrane structure is asymmetric. So some nanofiltration membrane, thin film composite, and nanofiltration outer membrane. So this is you need to design this one. How many elements do we have? So this is your outer membrane element. So you can see the membrane is on the spiral round type here. So you can see the membrane. So this is the membrane, like a thin layer, which means 20 nanometers. So this 20 nanometer will separate water molecule and salt. So you can see the skin layer. We just say skin layer on this side. Then water molecule will pass through this one. Yeah. And then you have a support layer and produce the water. So as I mentioned, water molecule is 0.3 nanometer and salt is around 0.7 nanometer. And then your RO membrane, you have to design 0.6 nanometer size of your pore. And then you can separate your water molecule using this ultra thin skin layer. The rest of them is the support layer and the backing layer to support your skin layer. So that's the very much breakthrough of our polymer chemistry to design this kind of salt and water molecule design. So let's see video of this outer membrane, how this can create this kind of pore size.
To create a To create our standard spiral wound membranes, we construct the flat sheet membrane using hydronautics automated casting equipment. We begin the process with a fabric support base and then coat it with a microporous polysulfone layer. This provides additional support for the top 0.2 micron thick membrane barrier layer. This top barrier layer makes the actual separation to purify the water. The semi-permeable polyamide layer consists of a thin film of polymeric material, a few thousand angstroms thick, formed on a porous supporting material. Semi-permeable membrane skin is formed on the polysulfone substrate by interfacial polymerization of monomers containing amine and carboxylic acid chloride functional groups. Product's manufacturing procedure enables independent optimization of the distinct properties of the membrane support and salt-rejecting skin. The combination of these three layers makes a durable membrane flat sheet that is used in each spiral wound element. The membrane flat sheet is then combined with a sheet of feed channel spacer. This provides turbulence and creates space between the membrane sheets to allow uniform flow of the water to the entire membrane surface. The leads of membrane and feed channel spacer are then combined with a sheet of permeate spacer, which provides open flow channels for the permeate even under high pressure. The leaves are glued along each of the three exposed sides. And then rolled around the coiled tube. With the back of the membrane completely sealed to the edges of the permeate spacer, the feed water is forced through the feed channel spacer, contacting the front or barrier layer of the membrane. Clean water, or permeate, passes through the membrane surface into the permeate channel and then flows in a spiral direction to the center of the element and is collected into the coiled tube. Hydronautic spiral wound elements can then be loaded into pressure vessels and interconnected with additional elements to complete any number of design specifications. Once the end adapter is connected to the last element and the pressure vessel is sealed, feed water can be introduced and then treated. The feed water that does not permeate through the membrane becomes enriched in salts as it travels through the feed channel spacer due to permeate water being removed. Typically, 8 to 10% of the water is removed in one 40-inch long membrane element. The permeate water then flows out the end of the vessel and is collected as the product. And the reject or concentrate from that vessel may then flow through another vessel, producing more permeate. The remaining concentrate may then be disposed of as waste or partially recycled as the feed. Typically, 70 to 90% of the water can be recovered as pure product water.
So that's the how we create the polyamide membrane, RO membrane, and then you put into the element, like a spiral round type of the module and element. And then this one has around 40 square meter of the membrane surface area. So one module, it's almost we have $200. So this module, so you can produce the every day around 200 liter of the desalinated water. So how many elements you need in the pressure vessel? So you just connect like a Lego and connect your element, one pressure vessel, several pressure vessels, and then all the pressure vessel will combine as a one high pressure pump, several pressure vessel, and element, outer membrane. That's the one unit you can design. So if you know which membrane, which element, what's the flux RMH, what's the surface you need, how much unit you can produce, so depending on your pressure, and then you can get your number. Okay, we need to buy this element, 1,000 element, 2,000 element, 3,000 element, maybe 10,000 element for Sydney desalination plant based on your scenario. So that's how you have to design. So you need a lot of calculation there because osmotic pressure will involve this kind of calculation. Then you keep changing your water concentration, like the seawater was 3.5% TDS. And then one element, you have a pure water and the high brine water. So your concentration is high, which means osmotic pressure is high. And then go second element, third element. So you keep changing your osmotic pressure. So which means you need to design the different element, different water flux, different also uh, calculation of the desalinated water production, right? So we need to learn some basic fundamental study of the transport phenomena to calculate this kind of detailed osmotic pressure behavior and applied pressure behavior for your seawater desalination. So let's say mass transfer across membrane is diffusion. So we are like a nanofiltration. Your last membrane bioreactor was size exclusion phenomenon. So you have a micro size, the water is just pass through. Yeah. So this is size exclusion. So depending on the size of your membrane, your water is too small, so you don't have to worry about your diffusion or osmotic pressure. But this outer membrane or water molecule salt is too small, so we need to think about the transfer phenomena is diffusion. So it's like a diffuse. Water is diffuse. So they automatically try to make a most stable condition, like a most entropy condition to create like a sodium chloride. You put in the pure water, even though you don't have to mix this sodium chloride, they will diffuse automatically and then make a stable condition. Very same concentration is here and there in the bottom, right? So that's the how we call diffusion transport phenomena. Then you need to understand osmosis. What's the osmosis? And the concentration polarization. What's the concentration polarization? And what's the permeate flux? You need to design. Yeah. So that's the how we have to think about to design your detail seawater desalination. So this is a little bit different from your microfiltration, ultrafiltration, membrane bioreactor design. So let's think about this one. Osmotic pressure. So you have a feed water here and brine. The brine has a very high salt. So which means your osmotic pressure is high. So let's say this is the membrane in between. Our membrane is here. So this is high concentration. So you have a more high concentration, high osmotic pressure. So water molecule will pass through your membrane because of the delta pi, which means osmotic pressure difference. So water is going through this high concentration to make a same concentration phenomenon. So we just say diffusion osmotic pressure. This is a forward osmosis. So high concentration, low concentration, depending on the concentration difference of the salt, you have a osmotic pressure because of diffusion. So we just say forward osmosis. Reverse osmosis means you pressurize the here, high concentration side, like a seawater, and then you push back to your osmosis, and water molecule will pass through this side, low concentration, which means the permeate, and you have reverse osmosis. So that's the we call reverse osmosis. So forward osmosis is just naturally occurring. So let's think about where is the forward osmosis in nature. So our kidney, we have a kidney here. So we have a blood stream and moving around our body. And then our blood goes to kidney. And this kidney, what's the function of kidney is you have a high concentration of salt. And then your blood is like a membrane, like a reverse osmosis membrane. And then going to your kidney, then your kidney has a very high concentration of salt, which means like a urine. You have a urine. Urine concentration is around osmotic pressure is 10 bar. So your blood, some of your waste of your blood stream is coming out, like a sodium will move to our kidney, and then your bad waste will pass through your kidney, and then your high concentration of osmotic pressure will separate your bloodstream concentration and your kidney concentration, and then you have a lot of water coming to your bladder, which means the urine will be discharged from your body system. So your blood stream will be make it cleaner because of your kidney, because this kidney keep trying to osmotically remove your bad sodium chloride or bad contaminant in your bloodstream, right? So that's how you can have an osmotic pressure in your body. Also, let's think about trees. So trees, how they sucking the water molecule. The tree is like a membrane, like a reverse osmosis membrane. So they have leaves and the roots. The water molecule, when they have rainwater, so it's coming through the leaves, even roots. And then tree has their own liquid. So this liquid has a high concentration of salt. So this salt will suck from your membrane on your leaves, even roots. Then water molecule and the nutrient like the sodium and or nitrogen, phosphorus, or some of the nutrient can be observed. So this is the osmotic pressure you can utilize in our nature. The trees, human bodies, we are all like a cell, and osmotically we just form. Naturally, we just have this kind of separation. So if you see this cherry, so cherry has also membrane cell in the skin. So this is membrane. And then water molecule pass through the cherry skin. Yeah. And what happens is that during the raining timing, so this cherry can absorb and pass through your water molecule inside, because the sugar inside the cherry has a very high concentration of the sugar. Sugar means it's a kind of salt, and then you have a osmotic pressure. So this osmotic pressure will suck continuously your water molecule during the rainy timing, and then continuously swallowed and swallowed. And then suddenly it damaged because of too much water in your cherry. And then keep growing, and then you can not tolerate for your heavy or your volume. So that's also one of the way. Also, you can see when you have your bathroom, in your bath, so you put your body for a long time, let's say 1 hour. So what happens in your body? So your body is swollen. So if you see the skin in your finger, so you can see the water molecule observe your skin, and then your skin is swollen than before your bath, right? So what happens? This is osmotic pressure. Your body has your own way of the salt inside. Then your skin is a reverse osmosis membrane. Then you stay there inside bath for 1 hour and long time, and then your water molecules keep accumulating in your body, and then you keep swallowing your body, right? So that's how we just have a osmotic pressure. But our bloodstream is a very low concentration of the salt. Let's say less than 1 gram per liter of the salt. And the seawater has a 35 gram per liter, 3.5%. So what's the osmotic pressure? Let's say sodium chloride, 1 gram per liter is around osmotic pressure 100 kilopascal, which means 1 bar. Yeah, so 1 bar is around 100 kilopascal. So sodium chloride, 1 gram per liter is around 1 bar. So 2 gram per liter would be 2 bar. 10 gram per liter would be 10 bar, right? So they have a concentration increase, osmotic pressure increase, and sugar is organic. So you have a very low osmotic pressure, like compared to 1 gram, and sucrose sugar is 1 gram. The osmotic pressure is 0.01 bar, 1.5 kilopascal. So depending on the ionized form, sugar is not really ionized, it's just dissolved. So you cannot create the very high osmotic pressure. So if you want to create the osmotic pressure, it has to be ionized, like a salt, inorganic salt has to be a very high osmotic pressure. So seawater, 35 gram per liter, 35,000 milligram per liter. Osmotic pressure is 27 bar. 27 bar. So which means you have osmotic pressure 27 bar. And then you want to separate water molecule and salt. So you need to overcome this osmotic pressure more than 27 bar. So, okay, you pressurize your seawater 27 bar, which means you are still same as your osmotic pressure of seawater. So you cannot separate. You cannot separate your water molecule because you have a osmotic pressure and applied pressure is equal. But you pressurize the 60 bar or 70 bar. So you have a double size of osmotic pressure. That's why you can push through your osmotic pressure beyond, and then you can separate your water molecule and salt. So that's why the osmotic pressure is very important to design your seawater desalination because you have a recovery. So seawater is 35 gram per liter. So you have to recover 10%, 20%, 50%. So your salt concentration increase, your osmotic pressure increase. So you have to apply pressure has to be different, and then you have a different water flux coming out, right? So how you can calculate varied condition of your salt, the flux, and the osmotic pressure, right? So that's the reason why you need the computer because it's you cannot continuously calculate using your hand calculation because so many changes there, right? Every step you will have a change. Your feed water, permeate water, also applied pressure is keep changing. Osmotic pressure is keep changing. So handwriting, yes, you can do that, but it takes time and a lot of mistakes will happen. That's the reason why we need to use this software to make much more easier than your handwriting calculation. So that's the osmotic pressure. We need to think about the osmotic pressure. This one was the first Nobel Prize in chemistry. So the the Van Hoffs, he developed this equation 1901 as a osmotic pressure calculation. It's very simple. It's a pi. Osmotic pressure is equal to C, concentration, and R, it's a ideal constant. Yep. And then temperature. So you have a more high temperature, you have a more dissolved your iron because of solubility of your iron. And then you have a more high osmotic pressure. High temperature, high osmotic pressure. Low temperature, low osmotic pressure. So you remember just before I mentioned about when you have a summertime temperature of the seawater 25 degrees, so you have a high water flow because of the viscosity is low. Then with the time viscosity is high because your water molecule, when you have a low temperature, they are very difficult to move. But you have a high temperature, they are easily they can move. But osmotic pressure, let's say high in the CRT, osmotic pressure, seawater 25 degrees, yeah, and 10 degrees. So you have a high osmotic pressure, high temperature, osmotic pressure is high. So which means osmotic pressure high, then you have to push your pressure more, which means your water flux is low, right? But your physical characteristics of the viscosity is more important than your osmotic pressure. That's what it is. Overall, even though osmotic pressure is low and the water is flux is low, so which means the viscosity is much more bigger impact than your osmotic pressure. So high temperature will have more flux. Even though you have a more osmotic pressure, it's supposed to be less water flux. So viscosity is a more limiting factor than osmotic pressure. So you can calculate osmotic pressure. It looks like a simple. Pi is the CRT. It looks like a simple. When you have a very single compound, like you have only sodium chloride, right? So sodium and chloride, so you have a concentration. I is the single ion. So sodium concentration 25 grams per liter. Chloride concentration is also equivalent 25 grams per liter, something like that. So you have osmotic pressure this much. So you can easily calculate. Problem start when you have a complicated compound. So seawater, how many ions you have inside seawater? Yeah, more than including the organics. You have a more than 400, 300 elements inside seawater. So you have to put every single compound, sodium, chloride, magnesium, boron, potassium, every single compound. You have to calculate if you want to know everything. But for most studies, not to calculate one compound and what so we can roughly when you design, let's say it was 35 grams per liter, it was the TDS osmotic pressure is 27 bar, right? It means like 50 grams per liter of let's say double. Because you have a 50% of the water recovery of the seawater desalination. So 35 grams per liter brine will be 2 times because of 50% recovery. So which means 70 grams per liter of your brine will be produced. 70 grams per liter of your seawater osmotic pressure will be double, which means 27 multiplied by 2. So 54 pressure, you will have a brine. So when you calculate your pressure, so you want to design 2 times 50% of equal, right? Then your osmotic pressure from 27 bar, and then double concentration of the brine will be 54 bar. So minimum you have to pressurize at least 54 bar for your applied pressure. So which means you can also calculate, okay, how much water will be lost, then how much we can overcome your osmotic pressure. So based on that kind of the calculation, you cannot do all the things. So when you have a detailed concentration of osmotic pressure, very detailed of the specific ion. So you can put into the water quality. This will give automatically calculate osmotic pressure in your software. That's why you don't have to calculate using this equation, which sodium and what's the pressure, and the chloride, what's the pressure. So you don't have to calculate one by one, right? Because software will give you overall data of the osmotic pressure and then they will calculate for you. Yeah, but theoretically inside, if you look at this software, so they are calculating such a way of all the detailed specific ion. So utilizing this equation and then make every single movement like element. Then they keep calculating osmotic pressure and how much water fluxing and how much you increase your overall concentration. So how they behave, change of the. So that's the reason, you have to understand how this software will calculate osmotic pressure with time. Yeah. So that's how we have to understand osmotic pressure. Also, we need to understand this. We have 12:30. So you wanna have a lunch? What time you wanna go for lunch? 12:30 or 1 o'clock? Now we can decide now, so whether we can go for another half an hour if we have more energy, and then if we don't have, we can have now relax and then have a lunch now and come back. What they like. Or you want to have break? Yeah? Okay, so now is we can have a 1 hour lunch time. Yep. So you can have a lunch and then relax and come back 1:30. So we can possibly finish. We have around 100, more than 100 slides to go. So based on this calculation, so we have to understand all the theory behind your software. So tomorrow, so when you do software, and you will understand how the software is keep calculating based on the today's theoretical, fundamental study. So, okay, we will come back 1:30, and then in the afternoon, I will go a little bit faster, and then we can finish on time by today. Any questions so far? So far in the morning session, any question? No? Okay, so see you 1:30 and then have a nice lunch.